Now let's try a couple of problems where we're using conservation of energy to solve for some unknowns. In this problem, we have a 3 kilogram crate that's going to slide down a ramp at a loading dock. The ramp is going to be 1 meter long and inclined at 30 degrees. The crate's going to start from rest at the top of the ramp, slide down that ramp, and experience a 5 Newton frictional force as it slides until it gets down to the bottom. Again, we are going to use energy methods to determine the speed of the crate when it reaches the bottom of the ramp. Now, when we say we're using energy methods, what we mean by that is we are using the law of conservation of energy, that the amount of energy that you start with has to be the same as what you end with. In this case, I'm going to choose the ramp, the crate, and the earth to be my system. If I choose those 3 things as my system, then all forms of energy in this problem can be identified within one of those 3 things. Also, I need to define a reference level. I'm going to define ground level to be my reference level where my potential energy is equal to 0. Anytime you're working with a problem and looking at energy considerations, you want to choose a place where the potential energy is equal to 0. We'll choose the ground. What that means is that as I look for the initial energy in the problem, I need to figure out how high the crate starts above ground. Because in this case, the initial energy that this starts with is a potential energy or a gravitational potential energy. It starts from rest, so it doesn't have any kinetic energy at this point. It hasn't slid, so there's no friction or heat that's being developed, and I'm just starting out some height above ground. Now, as I look at this triangle, if it is a 1 meter long triangle on this side and a 30-degree angle, I could set up a sine function where the sine of 30 degrees would be equal to this y position that I'm looking for, or delta y, height above ground, over the hypotenuse, and I'd find that this thing starts half a meter above ground. So when I look at my initial energy, I would start out with gravitational potential energy of mgy. Once the box reaches the bottom of the incline, there I would have some kinetic energy because the box would be moving at the bottom of the incline. And because there was friction on this ramp, the box would also be a little bit warmer by the time it reaches the bottom of the incline. And that internal energy is coming from the kinetic friction over the distance that this thing slides. So as I look at plugging some values in here, I can plug in the mass of 3 kilograms. I can plug in my gravity of 9.8, my y displacement of half of a meter. Again, mass is still 3. I'm looking for the final velocity. My frictional force was actually given to me, so I can take these 5 newtons and simply plug them in there. And I have the distance that I'm moving through along the ramp to be the 1 meter displacement that I'm moving through. If you take a minute and pause the video, you should be able to rearrange this equation to solve for v, plug in those values, and figure out how fast is this box moving by the time we get to the bottom of the ramp. Check your work and see if you get the same thing that I do here. You should get about 2.54 meters per second as the final velocity of the box. Let's try another problem. In this example, we have a block that is 0.8 kilograms that is going to be sliding across a surface at 1.2 meters per second. It's sliding to the right, and once it gets over here, it's going to collide with a light spring that has a force constant of 50 newtons per meter. Basically, this is our K value. Now we're going to start this problem by looking at our surface as being a frictionless surface. So whatever this is sliding across here as it runs into this spring, at first we'll look at what if there was no friction acting. Now the block is going to initially collide with the spring while it's moving at this 1.2 meters per second. And once it hits that, it's going to be compressing the spring. The question is, without friction, how much will it compress this spring by? Again, we want to use energy considerations. So as we look at this system being our block in our spring, we could again set a place where our potential energy is equal to 0, and I'll set that equal to the level where all this stuff is sitting, basically this tabletop or floor, whatever this thing is sitting on. What that means is as I look at my energy in the beginning and the end of the problem, there really is no potential energy, gravitational potential energy, because it's always sitting at my reference level where U is equal to 0. So if I look at the energies that are present in this system, this block is going to start out with some kinetic energy of 1/2 mv squared. And by the time we get to the end of the problem, where the block has now sort of run into the spring and the spring is all kind of scrunched up over here, all of this energy at the maximum compression is going to be the place where the block has finally stopped moving. So at the end of the problem, the maximum compression will occur when V is equal to 0, which means there isn't any more kinetic energy, and all I'm left with is the energy of this compressed spring. Now, if you think back a couple of sections, we talked about how springs have a stored elastic potential energy of 1/2 kx squared. So again, if I plug in some values, I know the mass of my object, I know its incoming velocity, and I also know K to be that 50 newtons per meter, I can solve for X and find out what is the maximum compression that this spring will go through. Pause the video, try it for yourself, and see what you come up with. As you plug those values in, you should find that you get your X equal to, just the X, not the X squared, you get your X equal to 0.152 meters. Now, the second part of this question asks, what happens if there is friction on this surface? So now we're not saying that it's a frictionless surface anymore, but instead, once this block runs into the spring, so it begins to collide with this spring here while it's moving at this 1.2 meters per second. As soon as it collides, there's friction now between the surface and this block, which means that as it's sliding across the surface and moving to the right, before it compresses the spring at its maximum amount, it's going to be encountering friction, which means that as we look at the types of energies that are present, it's again starting out with a kinetic energy of 1/2 mv squared. But in the end, that energy has turned into a compression of the spring, and it's turned into some friction or internal energy because of friction. Now, notice that I took this X for the compression of the spring, and in the place where I have that FKD, I called that D also an X because whatever the maximum compression of the spring is, that is the distance that it's sliding across the surface and encountering friction as well. So this would be the starting point of this new equation here. And notice that because you have an X squared and an X that you're solving for, you will actually end up with a quadratic equation. If you'd like to pause the video and try to simplify this a bit, go ahead and try that and see if you can solve for this new displacement or compression of the spring. And before you do that, think about what should this compression be? When we looked at the total compression without friction, we got about 0.152 meters. What should it be with friction? Should it compress the spring the same amount? Should it compress the spring more or less? Think about that before you get your answer. So go ahead and pause the video and see what you get for X. When you put this into, just start simplifying and plugging in the values that you would get a 25 x max squared plus 3.92 x minus 0.576. And all of that would be set equal to 0. So when you plug this into the quadratic equation, you would choose the positive root or solution to that, and you would get about 0.0924 meters. Notice that the amount that we get for X in the case with friction is less than the maximum compression without friction, which absolutely makes sense. When you have friction there, sort of sucking up some of that energy and turning it into heat, then the block is not going to compress that spring as much.